Now let us study about the limit state of collapse for flexure. So this is meant to analyze the reinforced concrete beam when subjected to flexure at the limiting state of its collapse. Now what are the assumptions in this analysis? Plane sections normal to the beam remains plane even after bending. So this assumption we have already learned as the Euler-Bernoulli assumption. What was the consequence of this assumption? The strain distribution in the reinforced concrete beam is a straight line. Now coming to the next one, the maximum compressive strain in concrete is equal to 0.0035. Now the next one, the tensile strength of concrete is completely ignored because we are supplementing with the material steel. Steel is being used to resist the moment on the tension side. So we completely neglect the effect of concrete on the tension side. Now finally, what is the strain at the level of steel? Since we are interested only in balanced or under reinforced concrete sections, so epsilon st, the strain at the level of steel which is subjected to tension, should always be greater than or equal to 0.87 Fy by Es plus 0.002. Now coming to the analysis of singly reinforced beams.
Here first we need to understand the difference between analysis and design. It is very important. What is analysis? By analysis we mean we know the beam cross section properly, we know the area of steel, but we need to determine what is the maximum load that can be taken up by the beam, what is the maximum moment that the beam can resist. So this is known as analysis. We know the cross section properly and we need to determine how much it can resist. But coming to the design, it is just the opposite. We know the maximum load that the beam can resist, or we know the loads which get superimposed over the beam. We need to determine the cross-sectional dimensions as well as the steel details. How much steel should be provided? What are the cross-sections of the beam? What are the dimensions of the beam? So such details are required to be found out in case of design.
Here we are going to define the cross-sectional parameters of a beam. A beam dimension, a beam cross-section is shown here, and let us understand what are the important beam dimensions. The width of the beam is an important parameter represented as B. The overall depth of the beam is represented by the letter capital D, and we have small d which represents the effective depth. Effective depth is the distance measured from the extreme compression fiber to the center of the reinforcement layer. And you have XU we have already defined. It is the depth of neutral axis measured from the extreme compression fiber. What about AST? That is another important factor. It is the cross-sectional area of the steel on the tension side. The area of steel which we see in this cross-section is the AST. Now before we go further into the analysis, we must thoroughly understand the limit state of collapse in flexure, for which we are considering the beam cross section and the strain distribution of this reinforced concrete beam at limit state of collapse, and also the stress distribution of this concrete beam at the limit state of collapse. For all this analysis, we are considering only under reinforced or balanced section. Now coming to the strain distribution, we have learned that the concrete fails at the same time as the steel yields in case of balanced section. So the concrete has a strain of 0.0035 and steel has a strain of epsilon st is equal to epsilon y for balanced section. But in case of under reinforced section, we must consider epsilon st is exceeding epsilon y. Epsilon y is given by 0.87 fy by es plus 0.002, which we have already learned. Now the depth of neutral axis is shown here as equal to xu. Since we are considering only balanced section and under reinforced section, xu is less than or equal to xu max, where xu max is the depth of neutral axis for balanced section. Since the effective depth is given by small letter d, then the remaining depth after we measure the depth of neutral axis is given by d minus xu. Now let us discuss about the stress distribution diagram. As we were discussing about the flexural behavior of reinforced concrete sections in our previous lecture, we were saying that at the limit state of collapse, the behavior of concrete stress strain becomes parabolic for the initial strains up to a strain value of 0.002, which you might have seen in the design stress strain graph of concrete, and followed which the stress value remains constant up to a strain value of 0.0035. So this is initially a parabolic variation, followed which it is a straight line curve. Up to a strain value of 0.002 you have a parabolic variation, followed which the stress value remains constant up to a strain of 0.0035. The design strength of concrete is given by 0.45 fck. So this value, this stress value is 0.45 fck. Now what about the stress on the tension side? We just have reinforcements on the tension side. We are completely ignoring the concrete on the tension side. So we bother about the stress in the level of steel. The stress at the level of steel we already discussed. For under reinforced sections and balanced section, it has already yielded in case of under reinforced section, and for balanced section it has just reached the yield point. So the stress at the level of steel is 0.87 fy, which is the design strength of steel. Now, knowing these values of stress and strain distribution diagrams, we are going to analyze the reinforced concrete section at the limit state. Now let us first find out the depth of neutral axis in the beam from the strain distribution diagram. The strain distribution diagram is used to determine the depth of neutral axis of the beam cross section. Now you see the strain distribution diagram. These are made up of two triangles. The strain distribution diagram is basically two triangles, and since they are similar in nature, because the interior angles are same in both the triangles, they can be considered to be similar in nature. Now how do we express the similarity? The opposite side by adjacent side of both the triangles are equated to find the depth of neutral axis. So we get an expression xu by d is equal to 0.0035 divided by 0.0035 plus epsilon st. So this expression you will get. To determine the depth of neutral axis xu, you want to find what is epsilon st. What is epsilon st? We know it is greater than or equal to epsilon y, or it is greater than or equal to 0.87 fy by es plus 0.002. Since for a balanced section epsilon st is a specific value, epsilon st is equal to epsilon y or 0.87 fy by es plus 0.002, we are first going to find the depth of neutral axis for a balanced section. So where we substitute epsilon st is equal to 0.87 fy by es plus 0.002 in the previous expression to obtain an expression like this. Xu becomes xu max, because we already said the depth of neutral axis for a balanced section is represented as xu max divided by d is equal to 0.0035 divided by 0.0055 plus 0.87 fy by es. In this expression we know XU max by D is a function of Fy. Fy is the yield strength of the steel. Yield strength of steel differs from one grade of steel to another. For Fe250, the yield strength is 250 megapascal. For Fe415, the yield strength is 415 megapascal, like that. And what is ES? ES is the modulus of elasticity of steel, which is given by 2 into 10 power 5 Newton per millimeter square. So these things can be substituted here. For a specific grade of steel, you can have a definite value of XU max by D. That is exactly what we obtain here. For different grades of steel, you get different values of XU max by D. For Fe250, it is equal to 0.53. For Fe415, it is equal to 0.48. And for Fe500, it is equal to 0.46.
You can refer to page number 70 of IS 456 to see these values there. Also, you don't need to by heart these values. You can actually refer to the Indian Standard Code on the page number 70. Now we need to determine the depth of neutral axis for an under reinforced section. For this, we need to determine the force which acts in the cross section. We know that the cross section experiences stresses. Compressive stress is experienced by the concrete and tensile stress at the level of steel. The compressive stress at the level of concrete shall result in a compressive force, and the tensile stress which acts at the level of steel will result in a tensile force. To determine the force, we know stress should be multiplied by the cross-sectional area. So let us first find out this force acting at the level of steel, that is a tensile force represented as T, is equal to stress into cross-sectional area. Stress, we know it is 0.87 Fy into what is the cross-sectional area of steel? It is represented as AST. So 0.87 Fy into AST gives the tensile force that acts at the level of steel. Now we need to determine the compressive force which acts at the level of concrete. For this, we introduce what is known as the concrete stress block. We know what is a concrete stress block. It is nothing but the compressive stress distribution at the level of concrete. So this distribution we have already studied, and we need to use this distribution to determine the force acting upon the concrete region. And we know two kinds of variations are there. One is a parabolic variation of stress followed by a straight line variation of stress. The parabolic variation will give a value of compressive force C2, and the straight line portion, the linear portion, gives another. The straight line portion gives another value of compressive force, that is C1. And by evaluating the concrete stress block, we can determine the compressive force acting at the level of concrete. Finally, you get the compressive force on concrete as equal to 0.36 FCK BXU, and this force acts at a position of X bar or 0.42 XU away from the extreme compression fiber. The extreme compression fiber is here, and the compressive force is acting at a location of 0.42 XU away from the extreme compression fiber. So we determined the compressive force acting at the section, that is represented as C, equal to 0.36 FCK BXU. We also determined the tensile force acting on the cross section, T, is equal to 0.87 F by AST. So one force is acting in this direction towards the concrete, the other force is acting away from the steel. So one is compressive in nature, one is tensile in nature, and these are separated by a distance known as lever arm. We know that the entire effective depth is expressed as D from the extreme compression fiber to the level of steel. And to find Z, you need this distance. This distance we obtained as 0.42 XU. So D minus 0.42 XU will give you the lever arm. Now, for any reinforced concrete section to be in a state of equilibrium, it has to satisfy the condition that the compressive force in the section is equal to the tensile force in the section. So one should remember always that the compressive force acting at the level of concrete should be equal to the tensile force acting at the level of steel in order to satisfy a state of static equilibrium. Now, if this condition of C is equal to T is satisfied, you can equate the compressive forces 0.36 FCK BXU can be equated to 0.87 FY AST. By equating this, you can determine the value of the depth of neutral axis given by XU is equal to 0.87 FY AST divided by 0.36 FCK B. So this equation is very important. This equation is valid only if the value of XU is less than or equal to XU max. So this is applicable only in the case of balanced section as well as under reinforced section. Now coming to the case of the analysis of over reinforced beams, we already said that over reinforced section is never going to be designed. But we need to know what if we encounter such a beam in the case of analysis. Given a beam cross section and its details of the steel area, and while analyzing you understood that the given section is an over reinforced section. It is not under reinforced or balanced, it is an over reinforced section. What will you do? So this is a special case. Just listen carefully. You have to follow a different set of procedures. Unlike the previous procedures to determine the depth of neutral axis, you have to follow a different procedure to determine the depth of neutral axis for a over reinforced section. So if you are asked to analyze an over reinforced section, or if you are asked to determine the depth of neutral axis of an over reinforced section, you have to follow these procedures. You see, in such cases, since steel may not have yielded, the stress in the steel shall not have reached 0.87 Fy. So over reinforced section, we learned that the beam section at the level of steel, you remember that the steel has not even reached the yield point by the time the concrete has crushed. So at the failure time, the steel is still not at the level of yield point. So the stress at the level of steel cannot be said to be equal to 0.87 Fy. So everywhere where we used 0.87 Fy in the case of under reinforced section, we cannot use 0.87 Fy in case of over reinforced section. For over reinforced section, it is not 0.87 Fy. We cannot take it as 0.87 Fy. So this equation cannot be applied. So this is also, T is also not 0.87 Fy into AST. Okay, but in the case of concrete, it is failing first, though, so we can take C is equal to 0.36 FCKB. So that can be taken, but never 0.87 Fy AST for steel. So the force at the level of steel is not 0.87 Fy AST, but force at the level of concrete is taken as 0.36 FCK BXU. Now what should be done to determine the depth of neutral axis here? Initially, a suitable value of XU or the depth of neutral axis may be assumed in case of the over reinforced section, and using that value you can determine the strain at the level of steel, epsilon St. We don't know the strain at the level of steel. To use this formula, this is known as strain compatibility formula. Epsilon St is equal to 0.0035 into d by XU minus 1. So once you know the value of strain, you need to determine the stress in the steel. So we know the strain in this level of steel, using which we can determine the stress
at the level of steel using the design stress strain curve of steel. So we know the design stress strain curve of steel, using which you can easily find out the stress at the level of steel. So let us say that stress is FST. If that stress is FST, then what is the force at the level of steel? Stress into cross-sectional area. If FST is the stress, FST into AST is the force. That is, T is equal to FST into AST. So instead of 0.87 Fy AST, we have replaced it by FST into AST, where FST was obtained from the design stress strain curve for the corresponding strain which we found out at the level of steel. Now, knowing the value of tensile force T and compressive force C is equal to 0.36 FCK BXU, you can equate them. C is equal to T to determine the XU value for the over reinforced section. By comparing these values of XU with the initial value assumed in the first step, if the difference between the two values is acceptably small, accept this value of XU. Otherwise, repeat the previous steps with an improved value of XU until convergence occurs. So we need the value of XU to converge. So until convergence occurs, we have to repeat this process. So XU value which you got here, we will use it again here, the strain compatibility equation, to determine epsilon ST, from which we will find FST. We will substitute in T, and finally we obtain another value of XU, and we will keep repeating this process until you get the same values of XU. Okay. So finally, we have obtained the depth of neutral axis XU, whether it be balanced section or under reinforced section or over reinforced section. If that is the case, we can find the final moment of resistance of the beam. The final moment of resistance, or the moment which can be resisted by the given beam cross section and the given steel reinforcements, we can find it out. If we know the force into lever arm will give you the moment. So we have two forces, compressive forces or tensile forces. We can use any one of them to determine the moment of resistance. Whether compressive force into the lever arm or tensile force into lever arm will give you the moment of resistance. The compressive force, which we know, is equal to 0.36 FCK BXU, and lever arm we knew, D minus 0.42 XU. So this obtains the moment of resistance of the beam. The other way to find the moment of resistance is using tensile force into lever arm, which is equal to FST into AST into D minus 0.42 XU. FST was used in case of over reinforced beams. In case of balanced or under reinforced beams, FST should be replaced by 0.87 Fy. Now, for the case of balanced section, how do you find the moment of resistance? And we call such a moment of resistance as limiting moment of resistance, given by mu limit. So the original moment of resistance was represented as mu. Here in the balanced section we represent it as mu limit, because we are replacing XU by XU max. So instead of XU, we give XU max for a balanced section to obtain the limiting moment of resistance of a beam.